Welcome back. Today we're going to talk about sampling distributions and how normal distribution is used again to discuss about means, and not just individual data points but means of distributions and what the central limit theorem says. So the biggest difference from last few chapter to here, or at least last chapter 3 to here, is that in last chapter we were talking about an individual value x of I, right? And that individual value x of I could belong to, let's say, a normal distribution that had a mean of mu and a standard deviation sigma. Okay, in this chapter we will start to look at the differences and focus on how to look at a distribution for a mean xi, and then you can take many means, just like you could take many data points to create a distribution and that was normally distributed. Here also you can take many means, it's going to be normally distributed with a mean mu, but now the standard deviation is not going to be just sigma, it's going to be sigma divided by square root of n. That's the big difference. Okay, so whereas in chapter 3 your z-score was computed based on x minus mu over sigma, in this chapter, or here forward, we're going to be computing z-scores based on usually means, right? Your x bar minus mu, but now the denominator is not just sigma, it is sigma over square root of n. That's the key difference. Okay, so this is chapter 3, this is chapter 7. So I want to give you an overview of what the difference is, so you can focus on that as we move along. Okay, so like we talked about, we're going to talk about the sampling distribution of the sampling mean. That's what we mean by the normal distribution with a mean sigma and a standard deviation of square root of n, square root of sigma over n. Okay, and we'll also look at some of the proportion information. So when we're computing the sampling distribution, when we're talking about sampling distribution, we're talking about the distribution of means. Okay, it's not just individual values anymore, it's a distribution of means. It's a probability distribution of the particular means. Okay, now let's start off with an example. You're looking at that miles per gallon example again. You have a new car and they're pre-production. You look at the mileage. You have two of them, and it's a 30 and 32 miles per gallon. The average is 31. Okay, so our mean is x bar is 31. You take 4 other cars and that mean is 31.5. Okay, now for each of those values the probability of occurring is 1/6. Okay, so because there is 1 out of 6 in that population. Suppose that all 6 cars was your entire population. Okay, so there's this probability of exactly 1/6 for each one of those values. There's no repeats. So then you could collect the mean. Okay, so you have one mean at 31.5. You have another mean at 31. Okay, so suppose I kept sampling different combinations of these numbers over and over, then I would get a distribution of different car mileages. Okay, if my sample size was just 2, okay, so I could pick 29 and 30, 29 and 31, 29 and 32, and so on, and then 30 and 31, and so on. Basically different combinations of the different values. Find their means. Okay, and then based on those means create a frequency and a probability distribution. This becomes your sampling distribution. Okay, so for individual x values, the probability is 1/6, 1/6, 1/6, 1/6, 1/6. But when you're talking about the mean of two samples, two different data points making your samples, then you see that it starts to look normally distributed. Okay, so that's what the central limit theorem really says. It says that if we keep taking lots of means, averages, okay, then the average, mu, of those averages is going to be closest to the population mean, mu. Okay. But it also says that the standard deviation of those means, sigma of x bar, so the standard deviation of those means, which is the spread of this distribution is of your means, is going to be less than the population standard deviation. So this has to logically make sense because your entire population contains all the values, all of it. Think about all your friends and their ages, right? That population contains all the values, so there's going to be some extreme points. Whereas if you make averages of 5 of your friends and take another average of another 5 of your friends and another average of another 5 of your friends and so on, and then you look at the spread of those averages, well, those average won't have that much variability in it as the entire population will, because the population has extreme points, whereas the average, those extreme points gets washed out because average is a central point, right? So the variation in those averages is going to be less than the variation in the entire population. Okay, and so it says if the population of the individual items is normal, then the population of all sample means is also normal. Okay, so that means if the population, so if xi is normal with mu and sigma, well, then x bar is also normal with mu and sigma over square root of n. But here's the more interesting part. Even if the population of individual items is not normal, then as long as you collect lots of samples, that's what central limit theorem says, as long as you collect lots of samples, your sample size is large enough, then the mean of that distribution will still be normally distributed, mu and sigma over square root of n as its values. So even if xi is not normally distributed, then still x bar will be normally distributed with mu and sigma over square root of n if n is large enough. That's the key takeaway from central limit theorem. Okay? So that's the general conclusion. Your mu is best estimated by the mean of your means, and your standard deviation of your x bar is going to be less than sigma. Okay, so that's the best estimator for your mean, and it's going to be your sigma over x bar is going to be less than that, but the exact connection is based on sample size. So this is to say that your standard deviation of your x bar is going to be equal to the standard deviation of all your data points divided by square root of n. Right, I just took the square root of both sides. Okay, so remember this, very important. Okay, so sigma of just x, an individual x value, is equal to sigma of the population, but sigma of the x bar is equal to sigma of the population divided by square root of n. So whenever we're talking about the mean and the spread of the mean, this is what you should be using. And these are hints I'm giving because there are questions on the quizzes and exams and homeworks based on this. When we're talking about an individual value, the spread of the individual value is basically the spread of the population, but the spread of the mean is the spread of the population divided by square root of n. Okay, so this is what you want to remember. And this makes sense, right? So it's to say that as my sample size increases, my mean will get more and more towards the overall population mean. And as my sample size increases also, my spread, my standard deviation of my averages will get smaller and smaller, so it becomes very precisely right on the mean. Okay. So as n increases, sigma of x bar decreases. It's inversely proportional, right? So to reduce variability in your data set, take lots of samples. Okay. Again, if you have any questions, feel free to email me about this. And these all hold as long as your samples are large enough. Okay, as long as your samples are large enough. And we mean large enough, typically n greater than equal to 30 is large enough. And that's what we'll go by. Okay. It also says that your big N should be very large, fairly large. Okay. Much larger than little n. Because the population is very, very large and usually means we can't collect it. But this is what you want to keep an eye out. Above 50 is great, but above 30 makes it large enough. Below 30, your normal distribution should not be relaxed, should not be used, and you should be very careful about using that distribution to describe the data set, because your n is too small, so you can't assume that sigma of x bar goes towards normal distribution with the mean mu and sigma over square root of n. So what does this mean in terms of pictures? When you're looking at, let's say, the population of individual gas mileages, it has a certain mu and it has, let's say, a standard deviation of 0.8. This is what the distribution looks like. Now, if you take some means of your entire population, take a mean of 10 different cars, take another mean of 10 different cars, another mean of 10 different cars, and then make the distribution of the averages of those 10 different cars and the other average of the 10 different cars and the other average of the 10 different cars and so on, and make a distribution of those averages, well then the average of that distribution will be right on top of the population mean. And if you took, let's say, sample sizes of not 10 but 5, then this is what the distribution will look like based on the initial spread, so it'll be much more narrower. And if you took, in fact, sample sizes of 50, much larger, then it becomes very narrow, almost towards the near population total. So keep increasing sample size from your population, take lots of averages, and then if you take the average of those averages, well, most likely you found out the average of the entire population, which is mu. That's the entire goal of this. Okay, is to figure out the exact value of mu, because we never know the entire population, and we never know the absolute average of the entire population. Okay. So if you go to that same example from chapter 3, we talked about x bar being 31.56 miles per gallon in that example of cars with a sample size of 50 and a standard deviation of 0.8. Okay, if you knew that the population mean is 31, which we don't know usually, but if you knew that, what is the probability of observing a sample mean that is greater than 31.56? Right? So we're trying to find out probability of x being greater than or equal to 35.56. But it's talking about a sample mean, right? So is it x or is it x bar? We're talking about x bar, right? The sample mean being greater than 31.56. So if I know that my sample mean is 35.56, well then maybe I can convert this to a z-value. And we know that z is equal to x bar minus mu divided by sigma over square root of n. So this is equal to 31.56 minus 31 divided by 0.8 over square root of 50. Okay? And that comes out to be 4.96. That's my z-value. So now I have to find the probability of z being greater than or equal to 4.96. It's very similar to chapter 3, just the denominator changed here, right? And we're talking about the mean here, not just the x value. And this you already know how to find. You just go to Minitab, plug in a z-value of 4.96, pick the right-hand side, right? A distribution that looks like this. Again, ignore my drawing, but a distribution that looks like this. You want the right-hand side at 4.96 out there, and you want all this area. Right, so just like we did in the previous example, you have sigma over square root of n. That comes out to be 0.113 when you divide 0.8 by root of 50. And then you find your x being greater than 31.56. So you convert it to z-value, x bar minus mu, over this whole value, which is sigma over square root of n. Right, this sigma over square root of n comes out to be 0.113. That's what we have in the denominator. That gives us to find the probability of z greater than or equal to 4.96. And if you go to the table or just go to Minitab and find the probability, you get the probability of 0.003. Just to reiterate what we would do in Minitab, that's up in graphs, probability distribution plot, view probability, right, the same steps. Okay, we have the normal distribution. Again, we're going to use the z-scores, so it's 1 and 0 there, 0 for mean, 1 for standard deviation. We have the actual z-value, and you want it to be right-hand side, right? If you remember, it's a right-hand side, and the value is 4.96. That gives us a p-value, the probability of 0.003. 0.00003, right? And if you can extend this wider, you'll see this gets to about -7, so there's a whole bunch of different values on the left-hand side. So it's almost 0. Okay, exactly almost 0. That's exactly what you get over here. So we then see that the probability of z being higher than 4.84, right? Probability of z being higher than 4.84 is very, very small, 0.0003. So almost fewer than 3 in 100,000 samples will have that large of a mean. Okay. So in basic words, what we need to take care of or make sure that we do is we collect lots of sample size. That will allow the distribution of the means to be normally distributed. Okay, so this allows the distribution of X bar to be normally distributed with a mean mu and a standard deviation of sigma over square root of n. So let's kind of do a few practice questions together. If in a large population of adults, the mean IQ is 112 with a standard deviation of 20. Suppose 200 adults are randomly selected for a market research campaign. The distribution of the sample mean is, the key takeaway here is sample mean. So it's talking about the distribution of X bar. And we said that the mean is going to be exactly the mean of the population, which is 112. So it really could be any of them. But the standard deviation is going to be standard deviation of the population divided by square root of n. So 20. So sigma X bar is going to be 20 over square root of 200. Okay, and if you simplify that down, you get 1.414. So you can tell it's going to be approximately normal with a mean of 112 and a standard deviation of 1.4. It's not exactly normal, it's approximately normal because central limit theorem said it's approximately going to be normal. The more sample size you get, the closer you get towards the normal distribution, but it's approximately normal. So this image kind of summarizes all of that information for you. It shows that the individual X distributions could look all kinds of weird shape, right? This is uniform, this has a decreasing, this increases, this looks like a parabola. But as you start to collect more samples and start looking at the X bar, the mean, right? So all of these are mean. The first one's just the X variable. But as you start looking at the means and collect more sample size, they all go towards the normal distribution. Okay, so let's consider a very large database of individual incomes from the Labor Statistics Bureau, and we take 100 samples of 1,000 samples of 100 incomes, calculate the mean, and make a histogram. And we take 1,000 samples of 25 incomes, so 1,000 different samples, simple random samples of 25 incomes. Okay, so n equals to 25 here, and here n equals to 100. And you do this 1,000 times for both of them, and you make a histogram. Which one of this is the one for the 100, and which one of this is the one for the 25? So just like we said before, when n is large, you have less variation, right? So the spread in that sampling mean distribution is inversely proportional to sample size, right? So when n is 100, there's less spread. When n is 25, there is more spread. So like we said, how large is large enough? You want to try keep n at least 30. That allows us to assume that there is approximately normal distribution with the correct mean and standard deviation. Okay, so if the population is normal, then your sample is, the distribution of your sample means is going to be normal irrespective of sample size. You don't really have to worry about sample size. But hardly will we ever know that the population is normally distributed. So we should always try to take at least 30 to make sure that a sample and the mean of those samples is going to be normally distributed. Okay, and now we'll sort of quickly review what we remember from Stats 2110 in terms of proportions. Okay, all this time we've been talking about means and standard deviations. There's also proportion P. that often we care about. Okay, so this proportion is usually, let's say, a percentage or a ratio. If you think about a fraction, that's a proportion. What fraction of your friends are females, or what fraction of your friends are males? Those are proportion. When we talk about it in terms of the population, it is just P. Okay, so for the population, it is P. But for the sample, it is P hat. Okay, now the key thing to make sure is that the number of samples that you get times the probability has to be greater than or equal to 5, or the number of samples that you get times 1 minus the probability has to be greater than or equal to 5. This makes the sample size large enough so you can assume normally distributed samples and make all the conclusions that we've been making so far. Okay. Now remember when we said that sigma, the spread of x bar, was sigma over square root of n, right? For proportion, it's a little bit different. Sigma over p hat is equal to the square root of p times 1 minus p over n. Okay, and if you don't have the population values, we'll have to use the sample values when we actually do this to estimate the population value. Okay. So let's end this chapter with a question. Hypoleukemia is diagnosed when blood potassium levels are low, below 3.5 value. Let's assume that we know a patient whose measured potassium levels vary daily according to the population distribution that's normally distributed with a mean of 3.8 and a standard deviation of 0.2. So that's, again, remember, normally distributed with the first number being mean, the second number being sigma. So we know that the distribution of the population is with a mean of 3.8 and standard deviation of 0.2. We're trying to find out if only one measurement is taken, what is the probability that this patient will be a hypoleukemic? That means we have to find out probability of x being less than or equal to 3.5. Okay? So I'll let you think about how to approach this problem then. Trying to find out x, you know mu and you know sigma. Think about what we've learned so far. While you're thinking about that, for the second part it says, if instead the measurements are taken on 4 separate days, what is the probability of an average diagnosis? So here we're talking about average, right? So right away you know then we're trying to find out the probability of now x bar being less than or equal to 3.5 is what you're trying to find. So for the first part, think about computing the z-score. Right, so that's x minus mu over sigma, which is equal to 3.5 minus 3.8 divided by 0.2, which is equal to negative 1.5, and we're trying to find out the probability of x being less than or equal to 3.5, which is going to be the same as probability of z being less than or equal to negative 1.5, right? We converted the x to z. And this, if you just go to Minitab, put in this value, just like we've been practicing, you will get about 7%, 0.0668. Okay? That's 7%. Now instead, if you're going to talk about the average, well then a z computation will be a little bit different. It's going to be x bar minus mu sigma over square root of n. Right, that's 3.5 minus 3.8 divided by 0.2 over square root of 4. 4 days is what we're talking about here. And if you compute that out, you get a z of -3. So we're trying to find out the probability of x bar being less than or equal to -3.5. Or is it positive? It's positive, 3.5. Well, that's the same as probability of z being less than or equal to -3. And again, if you go to Minitab and put this in, you get about 0.1%. Which comes out to be about 0.0013. Okay. So you can compute the z-value and from there find out the final answer. Okay, that brings an end to this chapter. Make sure you're keeping up with the homeworks and the quizzes in class. Again, follow on your assignments tab on Canvas to make sure that you know the exact due dates of all homeworks and assignments. Thanks.